An example of a photodiode amplifier design with data compression is discussed in this video. This circuit is implemented with 3 operational amplifiers and a pair of matched NPN bipolar junction transistors and also 3-volt Zener diode and standard avalanche photodiode that is basically operating as optical receptor and as optional temperature compensating 1 kilo ohm nominal value resistor if we want further temperature compensating feature in this circuit. Otherwise, using just a standard 1 kilo ohm is good enough here. Okay, so how does this circuit work? And then can we find a formula, closed form for the output voltage coming out of this circuit, which basically would indicate some level of signal compression for the received optical signal. Okay, so let's see. The optical signal comes and then it's converted with basically by the avalanche photodiode into a reverse bias current. So reverse current is passing through this photodiode and the only route it can go is this route. So that's the reverse current, and this current, which is the current of photodiode, varies from, let's say, 100 nanoamp minimum up to 10,000 times higher, up to 1 milliamp. So basically, you're talking about 1 to 10,000 scale. So that's the range of change in the current of photodiode, which is pretty large, very large dynamic range. Now, what the circuit is expected to do is it is expected to basically take in this very large range of the input current coming from the photodiode, depending on intensity of the light, and then convert that in a logarithmic fashion that I'm going to show, basically using a log amplifier, to an output voltage that, if the value of the resistors are properly set, then should basically just be log 10 the current of photodiode divided by the reference current that is defined by the circuit. So we will see if that is true and then what are the implications and what are the outcomes of this property. Can we prove it? How does the circuit work? So these are the questions that we need to answer. Can we find this formula? Okay, so first thing to notice, the Zener diode here, 3 volt. We have via resistor R, which is basically biasing that Zener diode. So let's say the value of this resistor R is 0.2. I'm going to write it here. So let's say the value of this resistor R is 0.2 kilo ohm to 100 ohm. Now what's going to happen is we have a 5 volt voltage at the input of the circuit for supply voltage, and we have 3 volt expected nominal value of the Zener diode. So the voltage drop across, nominal voltage drop across resistor R is obviously 2 volt. So the current that is passing through this resistor R, IR, can be easily computed. That current is, I'm going to write it here. So that current, IR, is simply equal to 2 volt, or basically just to make sure that it is written, 5 minus 3 volt divided by 200 ohm, which means the nominal value of the bias current for Zener diode is 10 milliamp, which is very good. So 10 milliamp current is coming downward for IR. Now, what else do we see? The Zener diode is properly biased with that amount of current going in a sort of a reverse bias fashion. So 3 volt is established. And then when we have 3 volt, that means then we have, as you can see, effectively a series of 100K and 200K here, because this branch out getting to the positive terminal of ideal op amps, which is not taking any current. So we know that this route and this route not taking any current. So as a result, what I can say is the current here is roughly on the order of, say, just 10 nanoamp or so. Let's say very small currents, that is the input, or basically close to 0. So now the series of 100K and 200K translate to 300K resistor effectively, and therefore the current that is passing this way, let's say referred to as I, let's say B1 or I bias 1, that current can be easily computed as I bias 1 is equal to 3 volt, the Zener diode voltage, and then divide by the 100K plus 200K, the value of the two resistors in series effectively, which means the current that is passing through these guys would be on the order of 10 microamp, which is 10,000 times larger than whatever very small amount of, let's say, input offset current that is going through the op amps that is negligible. So IB1 is 10 microamp, good enough. What is the benefit of this? Well, we have effectively 100K and 200K in series. They work as a voltage divider. So 3 volt comes in, and of course, it's naturally 2 volt will appear across the 200K resistor. That 2 volt will actually work as the bias voltage at the positive terminal of the two op amps, op amp 1 and op amp 2. So we have basically for op amp 2 and op amp 1, we have 1 volt sitting DC at the positive input terminal or non-inverting input terminal. With the proper operation of the circuit, these op amps are in linear region, so they have negative feedback linear region. So as a result of that, the negative feedback will enforce the virtual short for the op amp, which means the positive and negative terminal would have the same voltage, which is 2 volt. So therefore, that 2 volt will appear at the negative terminal as well because of virtual short between the positive and negative terminal. I'm going to write it here, 2 volt and 2 volt. If that helps to have a different color, then I'm going to just highlight that with the different color so that it's visible. Let's say here's the color. Okay, so 2 volt. Let me just also write it here. So 2 volt and 2 volt at the positive terminal. Okay, so what is the next move? The next one is we have effectively 3 volt. Look at this resistor here. So I'm going to highlight resistor 1 kilo ohm. On one side, we have 2 volt. On the other side of resistor, if we follow this trace, we end up hitting the 3 volt of the Zener diode. So therefore, what happens is we have effectively 3 volt here on the left side of the 1 kilo ohm resistor, and we have 2 volt. So there is 1 volt voltage drop, and that with the polarity that is shown, so that will result in a current that is flowing this way through this resistor. So I'm going to write that current as current I. Let's say if I name these transistors as transistor T1 and transistor T2, the matched pair of NPN BJT transistors, effectively this current is current of transistor T2, the collector current of transistor T2, this current, because it will go through the 1K and then can only go through the collector emitter of, let's say, transistor T2, and through the common emitter, and then through the output of op amp number 1. So that's the only route, because again, the input terminal of op amp cannot take any current, cannot provide any current, ideally. So therefore, what I can say is the current I2, I'm going to write it here. So the current I2, which is the current of collector emitter of NPN transistor T2, is equal to just simply 3 volt minus 2 volt divided by 1 kilo ohm. So 3 volt minus 2 volt divided by 1 kilo ohm, which means 1 milliamp current. All right, so this is effectively our reference current in this circuit. So via a Zener diode and via the voltage divider from the Zener diode, we actually establish a reference current in the circuit. All right, so what's going to happen then for the, let's say, connection of transistors T1 and T2 that are basically paired transistors. So by paired transistor, I mean these are on the same substrate, very close to each other on the substrate inside the package, and they are benefiting from the same junction and thermal properties. So for both transistors, so I'm going to write it here, for both transistors T1 and T2, using Shockley p-n junction equation, for basically p-n junction diodic equation. So p-n junction equation, I can write the current of, or let's say the voltage of base emitter for the NPN transistor is equal to roughly, for the silicon, let's say, type NPN transistor is equal to roughly the thermal voltage, which is roughly 26 millivolt at room temperature junction, and room temperature junction is on the order of, say, let's say 300 Kelvin. So roughly 290 to 300 Kelvin. Now, Vt times, that would be natural logarithm, so ln. And then we have the current of collector emitter divided by saturation current of transistor, which is thermally very sensitive. So we want to get rid of that saturation current because it changes a lot with temperature of the p-n junction of the transistor. So that's the benefit of having pairs like this, coupled like this way with a common emitter. It will get rid of that. So let's write, as you can see what happens in the circuit, we have the voltage of base of transistor 1 being routed via this wire to this node, which then is scaled up by the combination of 1K and 2.7K resistor to an output voltage for the op-amp number 2. So Vout2 will be defined by VB1. That's the nice thing. I need to find VB1. Of course, VB2 is 0 because the base of transistor 2 is connected to ground, obviously. So the base of transistor 2 has a 0 volt and the collector of transistor 2 has a 2 volt, of course. So V collector, VC2 basically, I'm going to write it here. VC2 is 2 volt and VB2 is 0. What is VB1? That is the question I have. So to find it is not difficult. I just need to write a KVL starting from, so I'm going to change the color. So starting from, let's say, if I go with the red color, I think it's clear. Starting from the base and then going this route, so base emitter. So basically what I'm doing is I am going through plus minus voltage of base emitter of transistor 2. And then from there, I have to, let's say, do a subtraction of these two base emitter voltages. So base emitter voltage of transistor 1, and then we'll get to base of transistor 1. So what I can write is this equation using KVL. So KVL or Kirchhoff voltage law at base of, let's say, transistor T1. BJT bipolar junction transistor T1. Then I can write voltage of base 1 is equal to VBE1 minus VBE2. Just a subtraction of the two base emitter voltages, given that the base 2 is grounded. So with that, then I'm going to substitute what I found and what is well known by the Shockley p-n junction equation. So if this is equation 1, I'm going to use it here. So then let's keep it. So using equation 1, I'm going to just substitute for VBE1 and VBE2 quickly. So voltage of base of 1 is equal to, this base, is equal to VT natural log. So let's just make it log base E, which means natural log. And then we have I collector emitter 1. And let's refer to that current, the current of, so see, I'm going to show with different color. The current of transistor 1 effectively is the current of the photodiode. So we talked about it. It's the only current that can come because of the light that is affecting the photodiode and causing that to generate a current. So I can just say I1 is basically I of photodiode. So I'm going to write I of photodiode for the current of collector emitter of transistor 1. And then in denominator, we have the saturation current of transistor, of course. So let me go back to the same black color here. So saturation current. For the second transistor, for the substitution for VBE2, again, VT, again, natural log, log base E. And then this time we have, as was mentioned, we are dealing with I2. That is, so I2 is going through the collector emitter of transistor T2. So that's why I'm going to just simply say, let me see, yes. So I'm going to simply say I2 and then divide by IS. The fact that the reason that I'm using same thermal voltage for both transistors and same saturation current for both transistors because I made the assumption, reasonable assumption, that these transistors are matched NPN BJT pairs in the same package. So that's important. Because of this, I can then, using the subtraction property of the log, I can just get rid of the most sensitive parameter or variable as a function of temperature. So therefore, I can write voltage of base of 1 is equal to simply Vt log base E, natural log, so log base E or ln, and then it becomes as simple as I photodiode, avalanche photodiode, divided by I2, which is our reference current. I said another name for I2 is I reference current. So if you would like to do that, we can also replace it with the reference current, I reference. Okay, so what is the benefit? Now, the benefit is I can just substitute for the reference current because we found the reference current to be already, it was computed. So there you go. I can, the value of reference current, not the, so to avoid confusion, reference current is I2. And I2 is found to be 1 milliamp. So I'm going to just substitute for that. So Vt log base E, let me just write it in a cleaner fashion, Vt log base E, and then let's name this as equation, say 0. So I'm going to use equation 0 here, and it becomes just IPD, or the current of the avalanche photodiode, divided by, let's say, the I reference, which is 1 milliamp. Great. Okay, so we got to the voltage of base 1, which is this node, voltage of base 1. At this node, in the middle of these two resistors, 1 kilo ohm and 22.7 kilo ohm resistors. By the way, it's recommended just for the sake of having better design, using, say, using good resistors with 1% or less, let's say, variability, which are decent resistors. It's not as if you're talking about very unique resistors. So I recommend using 1% or better. So less than or equal, let's say, 1% resistors with variability. The less, the better. Okay, so with that, now let's see, of course, given that the amount of the current that the base of transistor is taking, so this base of transistor, so I base 1, the current that goes through the base of transistor is very small. These transistors, they have beta or HFE, or the current gain, collector current divided by base current, on the order of, let's say, greater than or equal to 200. These are small current transistors. So therefore, if we are talking about on the order of milliamp current going through their collectors, then the current in the base or the current of the base would be on the order of, say, we're talking about 10 microamp or less, 5 microamp, let's say. So less than, let's say, 10 microamp effectively. So that's a very small current. And that's why we can neglecting and assume that the 2.7 and 1 kilo ohm resistors are effectively in series. So therefore, it's just a scale up from VB1 to Vout2. I can find Vout2 easily using voltage division here. So that would be then Vout2. So Vout2 is equal to just voltage division of between 2.7 and 1K and scale up from that VB1. So it would be 1 plus 2.7K divided by 1 kilo ohm times voltage of base 1, which is this formula, of course. So we can keep this as, let's say, equation 3. And combining, and we can also refer to this as equation 4. So the last one is moving from, and of course, we need to be careful about one thing that I forgot to mention. Given that the current of IPD is between 10 nanoamp and 1 milliamp, as I am showing on top, between 10 nanoamp and 1 milliamp. So it's obvious that compared to reference current, so take a look that I2, the reference current, is always 1 milliamp. So basically that means I1, which is the photodiode current, is always less than or equal I2. So I'm going to write it here. So maybe the best place to write it here, it would be I2 is the IPD, and we know that it is less than or equal 1 milliamp at most, greater than or equal 100 nanoamp minimum. So that's the property of the photodiode in this example. While the reference current I1, sorry, the name should be reversed. So that is I1, the reference current is I2. The reference current is just simply 1 milliamp. So you can see that I2 is always less than or equal I1. I'm going to remove this, put it here. We don't need it to, so put it here. And then I'm going to move these guys up so that there is enough space for the rest of formulas. There you go. So therefore, what I'm trying to say is I1, or the photodiode current, is always less than or equal I2, which is the reference current. So what happens is this equation, inside the argument of the log, we always have a number that is less than or equal 1. So therefore, the outcome of log is a negative number. So we need to be careful that VB1, so I'm going to write it here, this number is going to be less than or equal 0. So it's a negative number. So as a result, we need to recall that, therefore, Vout2, which is just a scale version of that negative number, is also a negative number. So I'm going to write it here as well. Vout2 is less than or equal 0 as well. So this is what we refer to as equation 4. Now, next move is the last one, going from Vout2 to Vout. So in the path from Vout2, or the output of the second op-amp, to the output of the third op-amp, it's just a matter of having one inverter, one inverting amplifier, which is this amplifier here. It's just a simple inverting amplifier, and basically for that, the Vout is simply negative 4.7K divided by nominal 1K of Temco. What I'm going to write is this 1K here is just nominal value. Effective value of the Temco is R Temco. It's a temperature compensating resistor with positive temperature coefficient. So positive, let's say, temperature coefficient of 3.5 pulse per million. So that translates, when it's considered that 3.5 pulse per million, will result in the value of this Temco with nominal 1K to be effectively 3.5 times the temperature, absolute temperature in degree Kelvin. So that is degree Kelvin. Assuming that this Temco resistor is thermally in close contact with the junction of these transistors. So that is easy to satisfy. When then that is the case, the value of RT is 3.5 times T. You can test it. For example, if you apply T equal to 290, which is close to room temperature, so 3.5 times, say, 290 Kelvin will give you roughly close to 1 kilo ohm. That is expected. So what I'm going to do is, as the last step, I am going to say voltage of output of op-amp 3 is simply minus the 4.7 kilo ohm divided by RT, the value of the Temco resistor, temperature compensating resistor. And it's optional, as I said. If we don't need this minor further temperature compensating, we can just use 1 kilo ohm for this resistor, and times Vout2. Now substituting using equation 4 for Vout2, and then using equation 3 for VB1. So using equation 3 and 4, the value of Vout3, or the output of the circuit, therefore becomes 1 plus, so 2.7 over 1K becomes just 2.7, and plus 1 becomes 3.7, of course. And then let's not forget the minus sign we have. Minus 4.7. Let's write it just 4,700. Minus 4,700 ohm divided by RT is 3.5 temperature in Kelvin T. And then we have the value of Vout2 from equation 4. So it will be times 1 plus 2.7. And finally, VB1 from equation 3 is going to be VT. And then we have log base E, or natural log of IPD divided by 1 milliamp. Great. We are getting to the last step. So if I continue that, voltage of the output of the circuit, Vout3, or the voltage of the third op-amp output, is simply then minus. So this value here is 4,700 and 3.5 T and times 3.7. That's the result of this guy. For VT, I am going to write it. It's known that it is 2.6 millivolt. So 2.6 10 to the power minus 3 when temperature is at room temperature. So therefore, what happens is I'm going to just, the best thing to do is I'm going to just divide it by, say, so as I said, this is room temperature. Then if temperature is more than room temperature, it will go up. So effectively what I need to do is I need to just scale up by, so divide by, let's say, 300 Kelvin times the temperature. So that's the adjustment for the value of VT. At room temperature is 26 millivolt. So now you see the benefit of that TEMCO, because we have one temperature showing up in numerator, and then we have one temperature because of that TEMCO showing up in the denominator. So it will start canceling out each other. I will cancel out to a very good extent. So log E, instead of log base E, I'm going to use a trick. We can write it as 2.3 times roughly. So that's why it's very close approximate, but I'm going to write it approximation of 2.3, and then we have log base 10. So change of base E to base 10 is easily possible, except that we need to have a 2.3 multiplier. So then we have IPD divided by 1 milliamp. So we are done, because what is happening is the beautiful property that this temperature dependency with this one is canceling out. So basically the TEMCO resistor here, to a good extent, gets rid of, practically speaking, to a good extent gets rid of the dependency on linear dependency on temperature, because of the thermal voltage, or VT, of the PN junction of the NPN transistors. So, and then the nice thing is the combination of rest of parameters here. So when you consider 4,700, 3.5, 3.7, and just the rest of the circuit here. So the rest of, let's say, parameters just end up to be close to 1. So effectively what we get, I'm going to write with different color. So we're going to get roughly very close to minus just log base 10 IPD over 1 milliamp, which of course we can push this minus into the argument of logarithm and then just swap the denominator and numerator. So finally, I can just write that the output of the circuit, or basically voltage at the output of op-amp 3, is log base 10 and 1 milliamp divided by IPD. That's it. This is what I needed to show. And this is the formula for the output of the circuit. What is the benefit? Well, we know that IPD, or the current of photodiode, so current of photodiode, we know that it is a value between 1 milliamp max and we have 100 nanoamp minimum, when we have a minimum acceptable light intensity coming to the photodiode. So with this minimum maximum range, then we plug into the formula, we can see that therefore the output of this circuit, let me use a different color. So the output of this circuit therefore will be greater or equal, when IPD is at maximum, which is 1 milliamp, we will have argument 1 milliamp divided by 1 milliamp, which will give us 1 inside the argument of log, which log of 1 is 0. So 0. For, let's say, minimum of IPD, 100 nanoamp, if I substitute IPD in denominator with 100 nanoamp, then 1 milliamp over 100 nanoamp is 10,000 times. And log base 10, 10,000 is going to be 4. So that's the maximum of the voltage. So basically, when we get this range of a voltage at the output of this setup here, then we are just showing that at 4 volt, it means the current of the photodiode has increased by 10,000 times to the maximum. So this means, so if we get 4 volt, it means photodiode current. So photodiode current is at max value of 1 milliamp. It means maximum intensity. And because it's a log scale, effectively what we are seeing is if I just sketch output voltage of this circuit as a function of, let's say, IPD, or the current of photodiode, the avalanche photodiode, then it looks like exactly a log scale. So we have, let's say, 0 volt. And the current of photodiode, let's say, let's just show it in terms of, let's say, microamp. So microamp. So minimum is, let's say, 0.1 microamp, which means 100 nanoamp, and maximum is 1000. So I am showing sort of a log scale, 1000 microamp, which means 1 milliamp. Then in log scale, we have we have 4 levels effectively, these 4 levels. So this is 1 microamp 10 times, this is 10 microamp, sorry, I need to just show it properly. So we have 4 levels that I need to show, 1 level, 2 level, and here 3, 4. So we have 1 microamp, we have 10 microamp, and we have 100 microamp. So, but what happens is we are increasing on a log scale, we are increasing actually linearly on a log scale. So here we have 1, here we have, let's say, 2, here we have, let's say, 3, and finally here we have, let's say, 4 maximum, as we talked about. So 1 milliamp, sorry, it's reverse. So let me make sure, yes, it's reverse, my bad. So we have 4, and the direction should be like this. At 1000 microamp, we get to 0. So I need to make correction here. And we have these values. At 0.1 microamp, we have the maximum voltage for this output of the circuit. That's why we are saying it's a compressed format, because on the x-axis, I'm showing in log scale, on y-axis is linear scale. In reality, if instead of showing log, let's say if I show linear and then log scale, if I turn it into linear scale, what it looks like would be something like a completely compressed version. So it would be like this. So that would be basically linear and then linear scale instead of linear log scale for the voltage versus current. So the current of the photodiode. And this is what is effectively the data compression or signal compression that I mentioned at the beginning. So we are doing a log amplifier. So using basically log amplifier. And the reason we say it's a log amplifier is because obviously you can see that the output of the circuit is a log base 10 function of the current generated by the photodiode. So it's a log amplifier doing the compression. So performing basically log compression. I hope that this example is helpful in terms of showing how a photodiode amplifier with data compression can be designed and how it can operate and what is the output voltage of the circuit. Thanks for watching.